Alright, today we're going to do more applications using exponential and logarithmic equations, and we're going to define what the half-life is. So the half-life, we've talked about doubling time, and doubling time is the time it takes for something to double. So the half-life is kind of the opposite of that. The half-life is going to be the time it takes for an initial amount to be reduced by half. So there's our definition. Again, the time it takes for an initial amount to be reduced by half. Instead of doubling, we are halving it. So let's do an example. We have carbon-14. It decays radioactively at a constant annual rate of 0.0121%. So we lose a teeny tiny bit every year. So we want to show that the half-life is about 5,728 years. So it takes 5,700 years for a specific quantity to be reduced to half its size. We don't have an initial amount here, but we don't need it. If I just say, if just to show you here, if I let Q0 be the initial, then if I want half that quantity, the final amount is going to be 1/2 of Q0. So when you divide half of Q0 by Q0, these are going to be eliminated and you're just left with the constant, the 1/2. So that's why if I'm talking about the half-life, the left-hand side is just going to be 1/2, and we won't really consider the initial amount. If I put it in here real quick, just to show you one more time, if I put the initial amount in, it doesn't matter what it is, but in the end, the Q0s are going to be divided away. So here's my quantity. Now I need the growth factor. It is decreasing at an annual rate of this number. So my growth factor, B, is going to be 1 minus 0.000121. And so we get a number that's very close to 1, and we have to write it out with a lot of decimal places so we can be accurate. We don't want to round up to 1 because that won't work. So my growth factor is that number. It's decreasing, so it's less than 1. 0.999879, and that's to an exponent of t. Well, what I'm going to do here is I'm going to solve for the value of t for the half-life, and hopefully it's going to come up to be roughly 5728 if I do this correctly. So my initial quantity goes away. We don't care about it. I have 1/2. I'm going to put that as 0.5 because it's easier to write. 0.5 is equal to the 0.999879 to the t. I can take the common log or the natural log of both sides. The natural log of 0.5 is equal to t times the natural log of 0.999879. So if I divide both sides by that, I'm going to get a final answer where t, I'm going to have to squish him down here, I think. T, I'll put him in blue so you can see him. T is equal to the natural log of 0.5 divided by the natural log of the growth factor, 0.999879. And in the end, you're going to find, if you put that in your calculator, it's approximately 5728. So if you look at that formula, and if we think about it, whether it's doubling time or half-life or tripling time or whatever, the ratio is going to be on the left-hand side, and it's just equal to the growth rate raised to the power of t. When it's annual and not continuous, the time actually ends up being the log of the ratio divided by the log of the growth factor. So here's our second example. We have a quantity, and it decays according to this formula. What does the E tell you? Tells you that you should have a continuous rate. Okay? T is in minutes this time. The half-life is 11 minutes, and we want to find the value of K. So again, I don't have a quantity, but I know that the half-life is 11 minutes. So that means the left-hand side is going to have a ratio of 1/2, and T is 11. So let's substitute some things in here. The half-life, 1/2 of the quantities are going to be equal to e to the negative k times 11. So we need to solve for k in this case. And since our base is e, it's a lot easier if you use the natural log. So the natural log of 1/2, or 0.5, however you want to write it, is equal to negative 11k times the natural log of e. And we know this is equal to 1. So we have the natural log of 1/2 is equal to negative 11k. And k is going to be whatever you get when you take the natural log of 1/2 and divide by negative 11. So k in this case is going to be approximately 0.06301. Now the negative sign is already up there. If I wanted to talk about the continuous rate is going to end up being negative 6.3%. So now we can take an annual growth factor and convert it to a continuous rate. And we can go back, we can go from continuous to annual. So what you have to look at here, I have something in an annual form and in a continuous form. The A's are the same, and the time is the same. So really, if I substitute in, if I want to set them equal to each other, my annual rate is equivalent to my continuous rate. Well, my A's are the same, and my T is the same. So if you look at that, what I'm saying is that B is equal to e to the k. We talked about this in the last unit. So my annual growth factor is equal to taking the continuous rate as an exponent with the base of e. So I can convert from one to the other. If I have an annual function, I know that because I don't have an e in it, and I want to convert it to a continuous rate. Basically, I know that b is 1.145. So I know that 1.145 is equal to e to the k, and I solve for k. To do that, I take the natural log of both sides, and that's equal to k times the natural log of e. Natural log of e is equal to 1. So in the end, my continuous rate is equal to the natural log of the growth factor. If you put that in, you get an approximate continuous rate of 0.1354, which is 13.54%. So let's look at that for a minute. My continuous rate is 13.54, and that's coming from an annual rate of 14.5. So they should be pretty close in value, although not quite exact. Converting the other way is even easier. If I start with e to the k and I want to convert to b, I know that b is equal to e to the k. So b is equal to whatever you get when you take the base of e and raise it to the 0.3, which is approximately 1.3499. So if I want to rewrite this function as an annual rate, it's going to be q is equal to 7 times 1.3499 raised to an exponent of t. And now I'm skipping to the last problem on the last page. Find the continuous percent growth rate of q is equal to 200 times 0.866t, where t is in thousands of years. So basically, I'm trying to find k. So I want to take this guy and convert it to an e to the k. My growth factor is 0.886, so I'm going to set that equal to e to the k. Hold on, let me erase here. e to the k is equal to 0.886. I take the natural log of both sides. K times the natural log v is equal to the natural log of 0.886. This is equivalent to 1, and you get k is approximately equal to, when you enter this in your calculator, k is approximately equal to negative 0.12104 if you took it out to all those decimal places. So the continuous percent growth rate, percent, is going to be decreasing by 12.1%. That's the continuous rate per thousands of years. So that's how we can use what we know about exponential equations to solve for continuous rate.